Okay, so let's start.
You just need to give me a click. Oh, no.
Yes.
Click here.
Okay.
Yeah, now.
Yes. Like always, what have we learned? So we learned about variational encoders and GANs, two neural network architectures for generation, mostly used for image generation. But we saw that we can use them also for some other stuff. Then variational autoencoders basically takes the core principle we saw before from the autoencoders and tweak it so we can generate it by sampling from the latent representation. And using the reparameterization trick allows us to use backpropagation there. Then we learned about training GANs with the adversarial game, two-player game, where they're trained against each other. You might remember the example with the fake money. And we saw some nice GAN architectures for different applications. And the last thing was that the GANs can easily be conditionalized to basically control from which class samples are generated from. And we can use this architectures for some other stuff, basically also some regression problems, that we can control some aspects of our generated samples. Today, we have a second part for deep generative modeling. And this starts with the year 2021. And there was actually a revolution in generative models. Before that, basically, GANs were the big thing. If you remember last lecture, I showed you how the number of GAN publications rose until 2017, and then people just gave up tracking. But in 2021, a new model came out. You probably have heard from that, DALL-E. And in between 21, 22, then DALL-E 2 came out. And that basically showed that for this certain aspects of image generation, these denoising diffusion models actually dethrone GANs as a go-to architecture. And you've probably seen that. Has anyone seen these nice pictures with an astronaut riding a horse? That was generated by DALL-E 2, which was developed by OpenAI, so kind of Google, I think. Microsoft. Who's Google? DeepMind. DeepMind, sorry. I always confuse these two. So yeah, basically prompt is astronaut riding a horse in a photorealistic style. And just from this text is able to generate this diverse number of images. And then also in 2022, some others followed, like Stable Diffusion, which is open source, also does this text-to-image generation created by a startup called Stability AI. And it's very fun to play with. Has anyone not played with something like this text-to-image generation? Everyone has played with that? Perfect, okay. So here I just said cat playing poker in the style of a painting from Rubens, Flemish painter, and you can see, yeah, it's quite nice, I would say. Very, very appropriate in both style, and you can obviously see the cats. And another one is Midjourney, which made headlines because someone used Midjourney, this text-based, another text-based image generator, to create an artwork for category was I think digital art and something like digitally processed photographs. And he entered this image there, and he actually won some prize. And yeah, that wasn't very well received, because then a debate came out about basically art in general, but also these models are trained, of course, on a huge data set of images with prompts, generally drawn from the internet. And of course, the thing is there images from a certain artist in this data set? Is it allowed to use it for training? And similar ethic debates like that. But I think we're going to push this a little bit to the side, since we're engineers. Let the other people figure it out. In our cluster, we have some people who are doing that, and let's see what these things can do besides just generating images. So what they can also do is, if you have an image, they can kind of enhance the borders about that. And that looks really cool. So I will just hope I can show you that. Yeah, and the browser here is yes. Okay. Yep. Where is it? Ah, yeah. Wait. There's somewhere here time lapse. There it is. So you can see how they basically shift this filter over the image, always have some part of the original in there, and then the model is basically able to fill out some blank part with something fitting. And of course, yeah, you always get multiple options, and then the designer can kind of select from one.
I think right now it's more or less implemented feature in the last version of Photoshop. So they really integrate software. Right now we can do this outpacking for
Yes. Yeah. Yes. Then there's in-painting. So-called in-painting is you can basically, by a text prompt or something else, you can take an image and you can iterate on that. So here, this very nice pink flamingo was added in there. You can see the rest of the image stays or almost the same. It's really hard to tell. And then you can take an image and create variations of that based on some parameters. So really, really cool stuff, especially for creative art processes. And so how does it actually work? So our goal here is, if you've seen the last models, like a variation autoencoder and a GAN, we always create some mapping between some sort of noise, our latent representation, and our images, basically our design space there. And instead of just trying to learn an arbitrary mapping like we did the last time, for these diffusion models, the idea is we start off with an image, and then in multiple steps, we add a little bit more noise each step. So start here. Fortunately, there's no image, but you can see here, you can still kind of see the face in there. You do that every step, add a little bit noise in this chain, and at the end here, you can see you get a kind of full noise image. And with that, we have a very huge advantage, for example, over GANs, because we have a mapping between an image and noise as training data. Even though it's really difficult training data, but we have also all the steps in between. So, and yeah, the trick there is also not to add a certain amount of noise on every step, but to vary that. So it's not important, but we basically have some schedule here that says for each step if we add more or less noise. And usually we have some progression that things starts out quite big and then gets lower and lower. And that's how we then reach this noisy image. Yeah, and what we assume is, not to freak you out with this expressions, this just says here, we assume that our noise is normally distributed. That's everything we need to know. And yeah, so we have this normal distributed noise. And then we kind of want to generate an image from noise. We kind of want to just reverse this process. So go in the other direction. And this has two very nice properties. First thing is we can kind of assume that the denoising step for every configuration, if we're here doing one denoising step, it just depends on our input image here and nothing else. So each step just depends on the previous one. We don't need the entire history. We just need the one step before. And that's a very common assumption in learning things. And it's a very important one because that makes it a lot easier if you just say, we just need the one state before. And the other one is if we have enough steps and our variance updates in each steps are small enough, we can also say that the reverse step is kind of similar to some sampling from some different normal distribution. There's a little bit magic involved, but it's very nice. So we have the noise process is kind of dependent on normal distributions, and the other way around, it's again just simple normal distributions, which are absolutely fabulous in dealing with mathematically. So that's actually how it looks like. We don't want to elaborate on that, but it basically just says that we have this normal distribution, and this just depends on here's the previous state, is this xt, this is previous state, then the time step itself, and that's it. That's all it depends on. And then we have this thing here, and that's actually our trainable network. So what we do is we have a network that takes this image here and then converts it in a less noisy image for the next step. And we do that actually with the same network again and again. So we start with noise. Let me see the direction. We basically start with noise here, and then put it in our neural network, get a less noisy image, put it again in our neural network, get in again in a less noisy image, and then we do that until we have our image. And the nice thing is we can actually use the same network. We just have to inform it about our time step. So what restrictions do we have for neural networks? Do you have any ideas? What restricts the neural network we can use for this step transition? There's actually just one. Our input needs to be an image. Our output needs to be an image of the same size. We can use autoencoders, yes. We can also use anything else. In practice, there's some autoencoder-like network structure that's called a U-Net. The greatest difference is that it has these. Okay. No, it's still running here. Okay, good. It has actually these so-called skip connections, where you basically, this is encoding, this is decoding, but in between you take some first stages from the encoding and just inform the decoder about that. That's all that's happening there. And yeah, he will talk about it in unit. I think I mentioned it. Maybe I mentioned it before. I'm not sure. It's from some. It's actually from the University of Freiburg here. Yes.
10 years in
yeah.
field of machine learning and its so-called segmentation.
Yes, and this has something between 60 and 70,000 citations. So yeah, and it's from some guy you might see at lunch at IPM. So we saw him today, I think. I saw him today. So question like always. Okay, how to get the labels in there? Any ideas? What did we do basically with the GANs and the autoencoders? We added additional input. Yeah, I think. Okay, good. Yeah, maybe. So what we can do is for each of these steps, this is just one step. Oh, not really. This is the diffusion model. This is one step, and each step gets a prompt. It also gets our time step, and this is a random number generator. So it just gets some randomly generated noise. The first one. And then we feed that into our diffusion models. Then we loop. At every step, we have, for our model, we have the time step as input, we have the prompt as input, and we have the image from the previous step as input. So we have 3 inputs there. And then then we're feeding it to the model over and over again, the number of different time steps we had. And then there's, in this architecture, which is for stable diffusion, I think, then there's a decoder. So to make it nicely, we are not working on the image representations, but we can also work on some nicer embedded representations, like we saw with JPEGs, that's some compression thing, or with the autoencoder, you know that we could scale down the number of features there. So we are using something like that there. So in the end, we need this decoder who converts this representation back to an image. So, yeah. Unit is the diffusion model here. That's.
So in this case, you repeat unit 50 times.
Yes. That means you have 50 time steps. Exactly. Thanks. If I remember correctly, ResNet is for classification, right? So the output is not an image. You need to have. Yeah.
There's only one part. You have images output, and the dimensions should be the same.
Yes. Other than that, you're free. So you can use variational autoencoders there, and you will see that you can also use GANs shortly. So if you look at all 3 architectures we have considered so far, you can see that they have different drawbacks and advantages. So the 3 main things we are concerned of is a high sample quality, then the diversity of the images, and that we're generating from all basically sub-classes there, or sub-examples, so that if we are training on cats, we don't want only black cats. We also want maybe calicos or striped cats or whatever. So we want to cover all diverse classes there. And then another thing is fast sampling. We want to not spend a lot of time to get our samples. And you can see that each of the 3 models covers 2 different of those. So GANs have quite good samples, and you can sample fast, but the diversity actually suffers. While variational autoencoders have good diversity, fast sampling, but the sample quality is often blurry.
You have seen that during the exercise, it's really impossible to get this round circle.
It's really sharp borders there.
Yeah, so that's the drawback of variational autoencoders.
Yes.
We'll have better results.
Yes. And the problem by GANs is if half your data set is, like I said, black cat, then you have a high probability that the GAN will learn all cats are black. And that won't happen with the autoencoders. And the third thing is with the denoising diffusion models, you have high quality of samples, you have very good diversity, but you need to process the image a minimum of 50 times. And UNet is not a small model, so it gets very, very big.
You probably have seen that if you play with journeys or that, how long does it take to image an image? It's not because of course, some limits on the server side, but at the same time, it's actually inherent problem of the models, the amount of computations needed to generate.
Yes. And they have quite good servers. There's a TensorFlow thing where you can download Stable Diffusion and run it on your own PC. I tried on my laptop, and it takes a few hours for 4 images, I think. It depends. I haven't set it out on the GPU or whatever, but it's.
If you try it on CPU, that's effectively why we want diffusion models on practice, because if you do it on CPU like we are doing variational encoders, one iteration will take more than, I think, 2-3 minutes. So just one image multiplied by 50, you get 3 hours.
Yeah, so that's at online you take 10 seconds. Okay. So what you can do here is you can, like I said, you can try to mesh things together. So GANs generate images, right? And you can feed maybe an image to the generator as some sort of noise. So we can use images in between there to do this diffusion step. So with here kind of forward diffusion steps, and what we can do is that we have a discriminator kind of compares a generated image to our real one, and thusly train, like you remember from the GANs, adversarially train them to learn this denoising step there.
Can I ask a question?
Yes.
If you can think about this image, I'm also.
Okay.
It's quite complicated. So already,
yes.
It's a state-of-the-art thing.
Yes.
You combine multiple architectures in one.
Yeah.
And if I understand correctly, in this particular example, what is happening, instead of UNet, you're using GAN, yes, inside, or not?
You're using GAN inside.
Yeah, okay. So that's another way
yes.
to do that, because GAN also takes a noisy image, and it's another noise, another the same size, but again, this is already quite advanced.
Yes. So, it's actually a little bit more different. So, what you do, you have this diffusion steps, and then you have the GAN here. The GAN gets your last image, your noise, and it creates an image. And then from this GAN-generated image, you do your diffusion, your noise steps. You add noise to them. And each of these noisy images, you compare to the other one. So the GAN just gets one noise image, and creates a real looking one. So
okay, it's hard.
It's hard. Sorry, it's a little bit different. But you could also use just a gun in each step. I also think I just understood it well looking at it right now. Okay, so what have we learned today? Yeah, that diffusion models are very fantastic for image generation. That the core principle is to add noise stepwise, so we can create a mapping between some noise image and some noise and some real image, and we don't have to learn this mapping from scratch. We can take every image-to-image model for denoising, and we can somehow combine GANs or variation autoencoders and the diffusion process to speed up sampling. Or I'm not doing anything, I swear. Tackle some of the issues the diffusion process has. Okay.
So on the next,
okay.
That's for the sort of theory. It's more or less everything about generated models, but you will see the big difference between generation and discovery in the next couple of slides or couple of papers. And what we will do next lecture, we will talk about active learning and what we call discovery. So you will see a little bit of difference there. But for now, what we want to do, because again, we provide you this state-of-the-art diffusion models, and the question how we can really apply them in, let's say, not for the images, because for images everything looks fine. How we can use it for something good. And there is a recent paper of our colleague from ETH. You see, it's great. It's not published yet as in a journal, but it's 1 month old. And what they're doing, they're trying to use the diffusion models for generation of nonlinear mechanical materials. I'm sure, I think I already mentioned a couple of times mechanical metamaterials, just a very brief explanation. The idea in mechanical metamaterials is that you use internal structure to define the properties. So, you know, when you have, let's say, alloys, like metallic alloys, you will, let's say, take some iron, you add carbon, and you get what you get? Steel, yes. And what's important in this case, it's amount of, first of all, it's important that iron is very stiff, like the properties of the carbon are also important, and also it's important what the proportional, what's actually proportions you're mixing. So idea of mechanical metamaterials is that you say, okay, I don't care about the properties of the components, but I care about the organization. So what you can imagine, yeah, we saw this from our paper, this thing, and I'm doing this a little bit weirdly, so correct, so let me draw it more regularly. So if you have structure, all of that, I don't want to make a mistake. A structure like that repeats itself. It will have negative Poisson ratio. Doesn't matter what you use as your building blocks as structs. Of course, there is some limitations. Use metal probably failed before, but in general, only geometrical arrangement matters. So mechanical metamaterials utilizes this idea, and just by combining things, combining some elements together, not chemical elements, or let's say having the sample and cutting the holes inside, because let's say you have this specimen with the holes, and you compress it, what will happen? Something completely unexpected. You will get something that looks like that. So it will be called instability-driven metamaterial. So by compressing this at some point, the circle shapes start to have this alternating ellipses. So, and what the guys are doing here, they say, okay, we would like to have materials, like with a very interesting organization, and would like to design them using this video denoising diffusion models. I don't know actually why it's called video denoising in this case, but it's the same models that Gary is talking about. So Gary, can you just
yes.
You can open, the paper itself. So yeah. Can close this one. Go to the lecture 10 and go to the Kaufman denoising diffusion.
Yes.
Make it.
Yeah.
Or maybe we can actually do it. Do you know how to make a full screen here? Okay, full screen off.
Yes. Okay. So, like Slava said, we want such a nice architectured material, and we wanted to have fit this to a certain stress strain curve. So, yes, thanks. So if we have our strain here and our stress, we might want to look at it like that. And in our data set, what they use, or in the data set they used, they had 11 points along this curve.
Are you familiar with this strain curve? Force displacement. You can treat this force displacement. Are you familiar? Okay, I do.
Good. Okay. And so 11 points there. And it's the basic goal. And for that, like Slava said, they used so-called video diffusion. I didn't touch anything.
That's probably something with the. It's
not Yes. So they used the so-called video diffusion generative model. And that's because they didn't just want the deformation path, but they also wanted the internal stress distribution. So if we get something like that, and we also might get some colored images that shows, if we do compression there, then it shows probably some stress here, concentrations. Probably, I'm not entirely sure. So we will have an image that shows us where our stress is located. You probably also have seen some of those. Some finite elements class?
I'm not sure, but...
You're not sure? Okay, yes. Then we can show you in the paper. So that's what we want to get. So yes, it's just some introduction to the metamaterials. Slava already kindly did. So let's go down and have a look at our data set. Because from a machine learning perspective, the three important parts are data set, model, and of course, evaluation. So, and yeah, here. So what they did to generate the data set, they sampled some probability distribution, is so-called two-dimensional Gaussian random field. It's not important what that is. The important part is it gives us quite nice distributions here in 2 dimensions that are connected and very well fit together. So we don't need to worry about a piece of material that's maybe, if we have something here, at some peak here, then it wouldn't be connected and that would just fall out, break off, whatever. So then we take this field, do just some binary thresholding. You can see how this evolves. And then we kind of, that's where our material is deposited. No. Yes. And the important part is that maybe some.
Can you remove the flash drive? It's weird.
Yes.
Okay, I will put my charger right down there.
Okay. These are connected to each of the sides. And from that, we can actually do some mirroring to get some very nice pattern here. And that's how they generated the samples for the data set. And then they took them and just applied compression here. And they applied compression not kind of on one element, but on an infinite row of elements by supposing this periodic boundary condition, which means that these repeat periodically infinitely. And for that, they did it in finite element simulations. And from that, they got these nice stress-strain responses from which they got the 11 points. And also, these are the images I talked about. So you can see red means high stress, blue means low stress, and yellow is in between.
So do you understand how it was generated? You actually, technically speaking, you can choose whatever method of generation you want, really. But in this case, this particular trick, when they do some, again, some three-dimensional thing and they cut it, due to some properties of distribution, you automatically have this periodicity. So you see that it means that you can stitch some of the elements. You can, for instance, stitch this one to this one and this one to this one. So it's kind of cool to have. And they copy it 4 times for one specific reason. In mechanics, if you have this nice periodicity, it's much, you can define Young modulus as one parameter. Because if you attended the class of micromechanics, you probably know that if you have arbitrary material, it can be anisotropic. So therefore, we need to have multiple parameters, like sort of stiffness tensor, to define properties in all directions. In this case, when you do the streak, you kind of see it's symmetrical. So for instance, it cannot do shearing deformation anymore. So this one cannot move here, and this one cannot move here, because everything is symmetrical. So this is just a purely mechanical trick. And then they put it to the finite. I don't know what's happening. But yeah, I double
Yes, it's probably.
So and then what you have the stress distribution, and depending on how much you apply force, how much you deform it, you have a different stress distribution, and therefore you have a different force response. So you deform it and measure what is the resistance of this material on this particular level. Question to you, just out of the curiosity. Why do you think there is a jump? No, they consider only elastic model. That's the thing, that's the beauty. The model here, let me just maybe try to do something like that. And maybe it will, at least will not do that again. No, they used elastic models, or hyper-elastic models, I would say. So it's not plastic. So what do you think happened here? Why is just jump? Yeah, it will explain something that looks like that. But this jump, any ideas by looking at this picture, what's happening? Kind of no, yeah, of course, something non-linear, but no, making can happen only in plasticity. Here you have no making. But look at this picture. Do you see what can happen? Instability, no, you don't have instability again. I will give you an answer. The answer is actually in this small notch. What's happening at some point, there is a self-contact. The material starts to contact itself, and therefore it's getting much simpler. So that's the reason actually for this jump, and that's actually quite beautiful. Then their model can detect. Oh, you will see that. Okay, go ahead.
Yes. Thanks. Okay, yeah. Maximum strain you can see here is up to 20%. And yeah, that's our data. So we have these structures as input, or we can parameterize it with this. And then we have our labels from the finite element simulation, both the stress fields and our stress strain response there. Okay. So this might look a little bit familiar, but we're going to skip it to this nice image. And for the video, what's happening is that they just stacked these here. So you don't have a single image. You kind of have a stack of images for a video. And then they did absolutely the same denoising, noise and denoising steps. So noise from here. You can see here a little bit that each part of the video is actually colored. Later steps, you can see a little bit green.
So
and
yeah, sorry. At the beginning, you have no deformation, so it's yellow.
Yes.
You have homogeneous zero stress field, and when you compress, of course, you start to have a stress. Then you kind of see it
Yes.
on the deeper layers, the deeper frames.
But
you see that it starts to show this.
Yes. It's really hard to see. And then you do here again add the noise, and back you do the denoising with the 3D UNet. For that, they kind of took just a regular UNet. And what's happening there is kind of gets again this stack of images, and it also gets this stress strain curve here. You can see here the 11 points, I think. And then they're not fed directly, so they kind of get into this embedding system, and then you can see that they're very intricately combined with this temporal attention layer. So that's again just some magic. Just treat it as magic. And yeah, what's important is this one. This one is just don't care. Okay, and with this, they were actually able to get very good results. This is just description of.
I think actually this paper, if people read it, it's quite easy to understand.
Yes.
Yeah, of course, we don't understand what specialization
Yes.
stuff, but in general, it was written very, very.
Yes. Most of the text is actually a description of the images we have seen so far. It's very, very nice because they go very much into detail. And what they did for evaluation is that they generated 4 distinct geometries for 4 curves. And then they took the geometries and did the simulation on them. And you can see here that this one are the predicted stress configurations for the structure by the diffusion model. And these are the ones from the finite element modeling. So they fit very, very nicely. Again, top row prediction, bottom row is the simulation. And if you look here at the curves, these are the red ones are the target dots it got. Then we have the curve from the finite element simulation. It goes very, very nice through our target points. And what's very, very much surprising even more is that this black curve, that was the best fit for our target points from our data set. So it learns to predict things that it hasn't seen very, very nicely. Similar here. can see it just, the simulation goes right through the target points. And again, the best match from the training data is quite different.
Yeah, I think I would like, what you did inside enough, I would like to repeat that again. So if you look at this top row, what's important, and when you did it, when you worked with GANs and with variational coders or CNNs, always interpolate in some sort of. So if you, let's say, again, if you have a cat, you interpolate images of the cat and try to predict another cat inside this. So usually inside of your training data. And that's why, remember when we talked about variational encoders, why it's important to match these probabilities, because if you are not matching them, you can get some random stuff. Here, it's very, very big advantage of diffusion models. In this image, do you have this?
Yes.
Yeah. They run, I think, 10,000 or I don't
know. I don't know. Yes.
10,000 simulations, and all the geometries actually give this gray and black curve. And they were able to predict with this model something going much, much higher and beyond the trained data set. And I would say this is not so maybe impressive,
next one.
This one is the most impressive thing. That's the best match that they had, this black curve, and of course mismatch in this case is 40%. But the model itself was able to predict what is the prediction? Prediction is triangles. Almost ideally what happens in reality on this sample. So that shows the potential of the diffusion models to go beyond the sort of the trained data set. And that's why they're really good for images, because you cannot train everything. So you can create a big data set of images, but what diffusion models can do, they can go beyond that. Yeah, that's really
yes. Cool. And so that's why this is really, really amazing. And yeah, it fits all categories very, very well. Yeah, and I think that's almost everything we need to know. It's just lots of this descriptions. Then there's a discussion where they basically say, this is really amazing and works absolutely well. And the only other part is that they were actually nice enough to promise to release the data with the journal publication, and that the code is already available. So you can find that on GitHub to retrain the entire thing. And
so it's one of the first, again, it's not one of the, yeah, I saw another paper, but it's one of the first very, very, very organized papers moved to the models of material design. And I think this one will be also very, I think it will be cited hundreds, thousands times more in the next, let's say, 5 years. It's very, very important. And to get published just once ago. So not even published, but Prince was published. So yeah, okay. So that's all about diffusion models, more or less. Do you have questions regarding this? It's technically speaking, it's a good question. For 11 points on the curve, I would not also use the diffusion models. I will use something quite simple. What they actually, the main advantage of that approach, they can show the video of stress evolution during deformation. That's something that would be almost impossible to capture using other methods, because of course you have the dependency between next frame and the previous frame, and also it's image. It's not 11 points. For 11 points, honestly, there are multiple papers that are showing much, not even better results, maybe, but comparable results with
very simple neural networks. Here, again, what's cool, they can really simulate these videos. They simulate how stresses are growing. They can simulate, even if we're not talking about the stresses, the shape of your material. So they can detect when it will contact. While initially, model, of course, has absolutely no idea when the contact will happen. Absolutely no idea. And you give a new microstructure there, and it gives you exact moment when it will have a stiffening. So that's a main advantage, in my opinion. So for the prediction of the curves, you're absolutely right. Absolutely right. It can be done much better.
I think the important thing there is that the curves are not predicted. Curves are the conditional label. So you get this LLM values to the network. It says, I want a geometry that has stress strain response that goes through to that.
Yeah, that's another thing that kind of
generate just generate some structural and we could probably use a version of autoencoder. We could probably use GAN, but we saw that these had drawbacks, and especially GANs for that are probably very, very unstable.
You have a problem with the training. That's the main thing. You're right.
For the choice of generative model right now, the best one for
But at the same time, yeah, you need to be careful, because if you can try a simple variational encoder or GAN on your computer, diffusion model is getting harder and harder to train because they are more and more advanced. So they have some estimation that it took them 70 hours on a cluster with 20 Teslas. So it's quite hard to. And again, it's quite simple task, you understand. And all DALIs, all these proper diffusion models for the images, they require enormous amount of computational time to really work. So yeah, but at the same time, when you train them, when they are there, and if they are available, again, they promise to make it available, but I'm not sure if they will do that. So then you can really play with that for different geometries. So that's for this diffusion models, that's all. But since we would like to wrap the generation models in general, what I would actually like to talk a little bit, first of all, I would like to give you a little bit maybe detailed historical, I would say, review of this U-Net thing that we discussed today. It will be very brief. Which one is this? This one, I think, yeah. Of U-Net. View full screen mode. Fine. The task was very simple. These guys used to work with people from biology, and the task was to do a cell segmentation. They have multiple cells in the microscope, and the task is to separate them. And I think we have a couple of images, for instance, from this microscope image. What you want, you would like to get borders, and you would like to separate cells in a very convenient and accurate manner. And so it's another example. So this is, you probably cannot even properly, it's weird, properly recognize the cells. Okay, on the left image, but the task of the model is to look at that quite nasty image and get you a very nice segmentation or maybe even coloring of them. So, and there was a competition on the similar topic in general, and I think they won with their model. They at the end, I think if you go, I like the last, I think, where is this? The last. Yeah, the authors of this algorithm have submitted 78 different solutions to achieve this result. So it was quite challenging task for them, but they came up with absolutely amazing idea that Gerrit already described you. So whole thing looks like that. So it's image to image conversion. And you have this input image file, of course, with black and white. So therefore, you have this one channel. And then you do 3x3 convolution and increase the number of channels to 64. As usual, we make it smaller and we grow this one. So important here, you use only valid padding. So because you don't want to imagine what happens beyond the border, so therefore your image will shrink. So you see they start with 572 by 572, then they have 57, 570, then 568 by 568. They do not add anything there. And also you will see what's happening. Then they do the max pooling, so they shrink it twice in size. Then you have increase the number of layers to channels to 128. Again, shrinking. So what's important? It's called, in this case, it's called levels. So it's not, cannot draw on that. Okay. So this is called levels. You start from this level and you go to this level, and then magic start to happen in this direction. So do you see something unusual in this architecture? Something very unusual. I think Gerrit already mentioned that. Can you create? I will give you a quick, very interesting question. Remember, in TensorFlow, we used sequential and functional definition of the models. Remember, when sequential was say model.add layer or something like that. Can you do it here, in your opinion? Or what will prohibit to do exactly that? Yeah, you have this so-called skipped conversion. So this layer, for instance, doesn't only have the information from this layer, but it also looks at corresponding layer during the encoding. And you see it's different size, by the way. So this layer is a little bit larger in size. So this one, it's 104, and this one, 36. So what they did, they cut the middle part and stuck them together. So this white part goes from here, and this blue part goes from here. Why they did it? Because they were a little bit afraid what's happening on the borders of the images. They didn't want to actually have the very high effect of the borders. So therefore, they always consider more or less central parts. And they did it multiple times while they're unrolling, decoding the image. And why it's important? Because technically speaking, the features that they learned here, that model learns in this level, are quite relevant to what's happening when you unravel. So when I looked how to explain that better, there is a very cool way to think about this particular problem. So first of all, what they need to do, they need to... Okay, let us look at the output. What they have as output, it's so-called output segmentation map. It's a 388 by 388 image with two channels. So they actually, with the two classes, they have a black or white. So each pixel belongs either to the cell or belongs to the background. And the idea that if I remove completely this side and I will keep only the encoder, what can I put here as an output if I forget about everything here? What can I do here? Classification. It's a classification task. Left side is just simple classification. So at the end, I have this sort of almost dense layer. It's still image, but very small one. I can actually flatten that and get some classification. So the left side, actually, since it's decreasing spatial information, you're losing the spatial information. If your cell is one corner or in another corner, at some point, you will go to this very small size and you have no idea where the cell is. So the left side actually answers the question, what? So what you are looking for, cell or no cell? And what's happening on the decoding level, this model starts to learn where. So you are right now not only no cell or not cell, you can say where this cell is located on your image. So that's a way to think about that. Of course, it's a little bit speculative way, but I think it's a good attempt. And this model worked perfectly. They have a very small amount of images. I think only 30 images. They did so-called image augmentation when they copied, rotated it in order to create more and more images. But in general, that was quite cool process. And there is not so many details here if you look at that. But at the end, the model, where is this one, performed very, very well in the competition. I think this is actually the ranking of the challenge, and you see there on the first place. They are a little bit better than the second model. I have no idea what the second model is, but they won the big competition with this particular model. But it took them quite a lot of efforts. So, and that's why U-Net is an extremely useful model for any segmentations, for anything that require you to detect cells, grains, or whatever you want. So segmentation, immediately, if you have the task of segmentation, think about U-Net. It's very well established model, and there are a couple of review papers just regarding this model. So you see, I think here is the amount of publications for the different medical fields: brain, pathology, cardiovascular, eye, and this is just a number of papers. It's insane. It's only in medicine. So, so this is for U-Net, but U-Net sort of doesn't generate anything. It's not a generative model. You can use it as a part of generative model, but it's not. So I looked for the different papers and just came up with a very recent review. It's first published, again, less than months ago. This is extremely massive review. It's still not published completely. You see, its article has been accepted only for the publication and is not yet published in the version of the record. And what you see here, it's a very good review of the different models that can be used in mechanics. And what you see at the top, on the blue, it's models that can be used to prediction. So you see our familiar friends, deep networks. We have the CNNs, we have RNNs. Do you know what is GNN? Have you idea what GNN is? This one? Graph neural network. So it's quite cool models as well. Instead of looking at, say, the neighbors in the pixel, like if you have images, you can actually look at the neighbors along the specific graph path. So in many cases, when you create some things that are related somehow, you can create the graph that will describe these connections, and then you can use it to learn. But we will not do that. So when you see what's happening in this case, you have a data with labels, usually, for this particular architectures. You have a supervised learning because you have a data with labels. So you use these labels to do supervision. And what that you can do, you can sort of predict properties, or if you kind of tweak it a little bit, you can do this inverse design. For instance, what we did with Gerrit, when you just do this tandem neural network, sort of very similar to autoencoder. The another class is of the models is something that we're right now discussing. It's variational autoencoder, it's GANs, and you see it's not even diffusions here yet, because it's like diffusions are very, very recent models. And you have data without labels. And you cannot use supervised learning. In this case, you used unsupervised learning, and you can do generation. So you can generate something that looks similar to your trained data set. There is another class. We never talked about that. It's called DQN, and now I realize that I have absolutely no idea what it stands for. Do you know? Deep some sort of networks. So this is so-called reinforced learning. And that's something that we will talk about next time, when we will realize what SKU stands for in this case. If you can see, it doesn't use labels, it uses so-called states and actions. So you can imagine that you have your, let's say, material or your system, and you try to make it better, or you try to learn how it functions. So the system itself tries different, let's say, configurations and see what would be the resulting properties. And that it learns itself by just doing some alterations. So right now, when we have a training data set, it's stationary. We have it and we do not touch it. When you have these models, what they do, they kind of they improve and improve and improve the training data set. They start with nothing, but then by measuring some properties, by measuring the performance of the model, they get better and better and better. So therefore, what you have here, it's states of actions. That's why it's called reinforced learning, because every time, let's say the model decides, okay, I would like to have these particular weights in my model, it gets immediate feedback saying, now you're performing worse. So it will say, okay, I will not use this weights and so on. And in this case, you have a very interesting output. It's material discovery. So do you see a difference between generation and discovery? How would you describe the difference between generation and discovery? Like any ideas in general, I'll ask if I will say, just claim that my model can generate materials or some geometries. And I will say that my model can discover some geometries. So what would be a difference in your opinion? Actually, the scheme is very clear to give you a hint. So how you would differentiate this? It's a no, I'm not asking about how exactly technically you are doing that. Of course, yes, you have a positive feedback, that's right. But in general, like, or on a more global level, what's the difference from the model point of view, let's say, or from your point of view, between the discovery and generation? Exactly. That's absolutely right way to think about that. Generation, it's the same as a training set. You have a training set, you just try to mimic something that looks similar to whatever you have. Here you have absolutely nothing. So you may have something, of course, at the beginning, but still you have no understanding, and you need to discover processes. You need to discover this relationship between structure by just doing attempts. Yeah.
I like to make it with how to do experiments. So generation is a little bit like fixed set of experiments, mostly random, but you could also do grid, and then you compare everything. You just say, okay, for this other experiment, discovery is basically one experiment. You get some results, and then you decide, I'm going to do this.
So your next measurement in this case, your next I think we call query, right, depends on the previous experience of the model, and that's why it's called again reinforced, because you have this sort of reward and targets depending on if you achieve targets, you get reward or you get punishment. So that's very cool, and actually we'll see a little bit of that even today. So there is in this review there's also very nice table just summarizing the use of the different generative models, especially in material design. So you know all these things more or less, but pros and cons allows the explicit control of the generation process, such as varying some attributes, easier to train and converge compared to GYAN. You already should remember that. The problem can produce blurry or low quality. Exactly. I'm just repeating what Garrett told you. So that means that we are correct, and these guys are supporting us. GYANs can generate high quality and diverse data that are indistinguishable from the real data, even for complex data distribution. I think we can claim a little bit like that diverse is not exactly correct in this case, but the problem can be difficult to train and can suffer from the mode collapse. That's a problem in GYANs. I think Garrett maybe mentioned that it generates the same image over and over again. It's completely ignoring the variety, diversity. It's just generating the same thing over and over again. We had a problem with the mode collapse in one of our works. And again, this transformer neural networks is the things that we discussed regarding the text. For some reason, they are here, and I will show you some absurd papers, honestly, in my opinion, and what they say, that state-of-the-art performance and variety of natural language processing tasks, allowing generating mechanical metamaterials using sequential data such as text. And of course, it's like, this is, in my opinion, honestly, this is it's very stupid. So can struggle with modeling rare or unseen words in natural language processing tasks, have no idea why it's related to materials, and require additional data processing to label the geometries for data set. It's a little bit more close to the materials. So, and I would like to show you example. It's a recent paper. They sort of, what they did, they just put sort of the text inside of the, I don't know, ChatGPT or whatever. Oh, not ChatGPT in this case. They put it inside of DALL-E or whatever diffusion models. In this case, actually, they get an image, they generate 3D models, and 3D print and test it. So then they have something that looks quite weird, because of course we know if we ask to generate hexagonal lattice, you get some random things. I tried by myself. These image generation models, they are not very good to generate something reasonable from the mechanical point of view. They will generate you nice images. Then, of course, you can tweak it and process these images, but in my opinion, that doesn't worth it, even despite this paper. And I actually can show it a little bit. Yeah, B1. I just, for now, I will highlight people. And this is MIT, actually. Paper, they like this stuff. Honestly, it will not work, in my opinion. It's just a hype. So they used a very interesting architecture, but that's actually really, they have a GYAN that generates image, and they also have this clip model that actually tries to understand how close the generated image to the text. So you generate image with this VQ-GYAN, and then you ask the clip model to describe the image. And then you compare how close your original text input with the generation, and sort of you do it in a loop until you get some final prediction. But what they have as a final prediction, it's quite, again, ridiculous in my opinion. It's something like that. Then they transform it to the 3D printable structures. They 3D print the structures. Nice, very nice. But I have absolutely no idea why anyone would like to use it. So fancy things, I think it's not, it's too early to talk about transformers in these particular domains. But what is actually good to talk about is this thing, pragmatic generative optimization of novel structural lattices, metamaterials with machine learning. And here actually I would like to do it with you together. So I will open that, but I will not show you anything on the paper itself for now. This is a different paper. And I would like to give you a challenge. Are you familiar with 3D printing? A little bit. At least you saw 3D printers. So the thing is, my task right now I would like to generate some geometries, some metamaterials or materials that will have high Young modulus. So they will be stiff. But at the same time, there is another parameter that is kind of related to Young modulus. It's called wave velocity. And again, ignore it, but we would like to minimize wave velocity because it will make our material much better in the case of impact. So it will accommodate more energy due to that. So high E and low, let's say called C. Honestly, in just homogeneous material, if you have the cube of metal, you will have C equal to square root of E divided by density. But we will ignore that because we will have very complex architectures. So how would you approach that? So I want to generate it. How would you present the geometry? First, a question for you. Yes, what would be the design space in this case? Okay, let's okay. Let's go like that. So I would like to do something similar like that. I would like to have a 12 by 12 pixels image, and I would like to sort of to assign each pixel either its material or is it whole. So because we want to have a quite high porosity in order to minimize C. So right now, inside of this each pixel, I say, maybe in this case, if it's a hole, You see, we will get a very nice hole here. If I will draw it, we will have something like a hole in this thing. So you understand how we can transform material or hole into the ones and zeros. It's very close to the topological optimization you're familiar with. So I have a 12 by 12 image with ones and zeros. What should I do next? What do you mean? No, I don't know. I don't want to. Okay, so what I would like to have at the end, I would like to have the material. I would like to actually have a description of 1, 0, 0. So how I build the material in this case. So I would like to put material. I'm just repeating that. 0, nothing. I would like something like that, something like that, something like that. One more. So what will be my material for when I will do 3D printing? So it will be, I think I will print it from here to here, start from the bottom and print it. So, but now my task is to find the material with the highest E and lowest C. How would you approach that? This is just a way to store information about our structure. So 1, we put the material in this pixel, 0, it's not. At the end, our material is just whole image like that. How would you approach that? Okay, yeah, you can. So we simulate what? Oh, but what design? We don't have any design yet, so we need to kind of come up with some design at the beginning. No, we know that our materials will be stored as this 12 by 12 matrix with ones and zeros. So we know that, but we still don't know which one of them are optimal. So we have no idea which one would be the best one. But we can simulate it. We can take this matrix and put it into finite elements in order to get E and C. So we have our resources. So we take our matrix, we put it in finite elements, and we get E and C. Yeah? Oh, it's hard. You on one of the proper way to do that, but it is hard because how can you say that this pixel, for instance, is important or not important? It's important depends on the neighbors. So you cannot really do, and we don't want to. Yeah, we kind of can remove. Yes. So another approach, very similar. Wait, come again? And. Okay, you can do that. It will be a topological optimization. It would be exactly topological optimization. You really just gradually trying to make a material better. But how can I use some sort of machine learning tools here? Come again? Oh, okay, we have no idea about reinforcement learning yet. Yeah, okay. That's right. That's right. Okay. All in a kind of correct way, but simultaneously not the way I want. That's a problem. So let me, in this case, talk about the approach that I would like to share, and that actually was published here. So the idea, absolutely right at the beginning, that you just create some random. So if you have access to finite elements, and you can 0, 0, 1, 1, 0, 0, 1, let's say 1, 1, 1, 1. And you can generate random things and run them through the finite elements to get E. So let's say it's a sample 1. You have E1 and C1. And you can have a sample 2, whatever. So what you can do afterwards to replace finite elements. Because finite elements are extremely computationally expensive. So if you have ability to run, let's say, 10,000 of the simulations at some point, what you can do then? We did it already once in Home Project 1 in particular, actually. You can train a model. You can train a more predictive model. You can train a model that predicts E and C, and you don't care about finite elements anymore. You can actually give this model to anyone without access to COMS or Labacus or ANSYS, and this person will be able to say, okay, I would like, what will be the properties of my materials and so on. Do you see any problems associated with the 3D printing? So we print from our material, and we print it, start here, and then gradually it's growing. Do you see any problem for our geometries? Yeah, it's not actually in this case porous structures. You still can do some porous structures, but the problem that you cannot do something like 0, 0, 0, 0, 1 here and then 1 here. It will not stand. So there is a lot of designs that are completely impossible for the 3D printing, and you also need to account for that. And that's a little bit of problem. While you can predict the properties, the problem of the generation is very clear. You generate something and it has no sense. You cannot produce it anymore. And that's a way, that's why the researchers in this particular example used a very cool technique. They combine CNNs. Oh, you see nothing because there is a board. So the pragmatic approach combines a genetic algorithm with a convolutional neural network to effectively invent manufacturable architectures. So we're talking about invention, and we're already talking about sort of discovery. And in this work, we show how machine learning guides discovery of new unit cells that are Pareto optimal for multiple competing objectives, specifically maximizing elastic stiffness during static loading and minimizing wave speed through the metamaterial during the impact event. That's what I say. So let's take a little bit of a look of what's the problem they have. Researchers often use analytical equations to physical insights from years of experience to generate ideas, and then use an optimizer coupled with simulations to parametrically optimize the metamaterial design. This method contrasts with traditional engineering design, which takes a top-down approach where the systems engineer starts with the gathering requirements, generating abstract conceptual designs of the system, and then iteratively converting the system architecture into the detailed design. So, and generally the literature lacks guidance on the de novo design of lattice metamaterials. So new designs that do not exist yet. So that's what we call discovery. In this work, we make no claim of having found the global Pareto. I will explain what's Pareto optimal set of designs, but instead focus on achieving better designs than those generated by the human intuition or by random guessing. Specifically, this work set out to identify the trade-off of lattice material properties between two competitive mechanical objectives. And actually, I already kind of explained you that there is a problem, inherent problem with these two objectives. We would like to have a high E and low C, while we know that some sort of they are connected like that. So therefore, if this is high, and so on. So, but for metamaterials, you can break this relationship a little bit. So they want to identify the trade-off, generate lattice unit designs that are Pareto optimal. Pareto optimal, I think it's time to introduce this term because we will see it on the next lecture. Pareto optimal means if you have two competitive functions, you cannot improve either of them without making another worse. So let's imagine that you have a plot like that. You have let's say you look into the Amazon and you have the objects and you have the cost here and you have the quality here. You can have something like that, and the cost, it's like inverse cost. So higher you go, So at this point, for instance, you can improve quality without changing the cost. Also, you can decrease cost without changing the quality. But at the same time, if you look at the external border, if you would like right now to improve quality, you can go only in this direction because you have no points here. And therefore, you need to make your cost higher. It's an inverse cost. So Pareto optimal means that if you have two functions, that you cannot improve one of them without making another worse. Is it more or less clear? We will talk about that a little bit more. So, and therefore, you need to find, you cannot find a material with Young modulus of, 1 terapascal and C equal to 0. They do not exist. But there are some optimal combination, optimal trade-offs. And these trade-offs called Pareto optimal trade-offs. And improves the overall computational efficiency. So what they provide, it's actually quite interesting thing. So That's what we were talking about. They generate the structure randomly, putting ones and zeros. Of course, they have some specific range of porosities. They don't want to have a lot of ones and a lot of zeros. I think the porosity is from 30% to 70%. And this, of course, cannot be printed. Like this part will not be printed. So they actually modify it a little bit to get printable models like that. They have some rules on that, and you see the print direction here, and then you see that this system can be sort of printed. There is, of course, it's hard to do if you are printing, but you know that you can do that technically. So what they're doing next, it's quite fascinating. So they have this structure. They create it, they put it, as we already discussed, in finite elements simulation, and you see how it deforms. So they get, first of all, from the top row, they have Young modulus, and from the bottom, you see the timing is very, very small. It's like milliseconds, or microseconds, microseconds. And that's why they used for impact for the characterization of the wave speed inside. And so, do you understand in general how to do CNN here? CNN here, it's absolutely basic. So you feed the image with ones and zeros, and you get your Young modulus on C. So there is nothing in terms of discovery, nothing generative here. So, and that's exactly what they're claiming. The first part, they say that it's CNN was trained on 45 epochs, and the training error usually decreases, and this is a training error that they show. It's good. So, but the problem is, based on the previous works, 3 approaches to using CNN exist. So right now, CNN acts as a surrogate model instead of finite elements. Nothing super extremely new. But then, what you can do, if you want to sort of generate things, you can use the CNN as a rapid screening tool. So you generate multiple designs and then manually say, okay, this is good, this is good, this is good, I will take this one. Yeah, it's kind of stupid. The approach number 3, and actually this is approach proposed by you, use gradient optimization to optimize the unit cells. The gradient can be obtained from CNN, since CNNs must be differentiable in order to train them. So actually, you can take these gradients and do sort of topological optimization of these gradients. Problem in this case that you may have the design that doesn't make sense, that is not printable. And that's a big, big issue because a lot of designs are not 3D printable. And if you do these optimizations using these gradients from CNNs, you may have some absolutely absurd results. So here, the proposal is to use the generic algorithms to optimize designs when the evaluation function in GA is in the generic algorithm is the CNN itself. Let me explain. It's very simple to understand what's happening here. So you generate some good unit cells called parents, and then you kind of randomly combine them together, creating so-called offsprings. You can see that you choose a random number that defines this line position, and you take this corner, put it here, you take this corner, put it here, you take this corner, put it here, and you take this corner and put it here. So you see how this unit cell is combined from this one. And this is inverse. So you have this one from this parent, this one from also this parent, and the bottom is from this parent. So you can combine these 2 unit cells in a new unit cells. And also you can add, it's important in genetic algorithms, a little bit of mutation. So you just, nice. Is it completely over? No, it's not yet. So you can add some random point, for instance, or some small modification. What they did, they modified they invert 10 pixels in this case. And that's what they actually are doing. So they get all previous, and genetic algorithm, we will talk about that, how it works. It generates some images, some structures, and then evaluate the best of them, select the best of them, and just do this crossover and mutation, evaluate how good they are, remove the things that are not printable, and repeat the cycle multiple times. During the time, you kind of your structure evolves and evolves and evolves and getting better and better and better. And what's important in this case is to look at this particular plot. So why do you think I cannot just run CNNs and pick on, let's say, when I train CNN, let's say I train CNN, I use 10,000 examples, I train CNN, Why cannot I very fastly run it 10 million times and just choose the best lattices? Why do you think it will be a problem? How many lattices do we have in total in this configuration? 12 by 12. How many lattices do we have? Come again? No, we have a 12 by 12 image with ones and zeros inside. How many possible configurations can we have? 2, and then? Not 12. It's extremely large number. Yes, it's extremely large number. You cannot really do anything with that. So that's why when you just run randomly, you will get very small selection of the lattices with probably very very average properties. We had this problem as well with these guys. So when we generated something, we run million simulations. At what we get something with approximately the same Young modulus and approximately the same speed, because we are random. So we never, for instance, one of the stiff lattices that can exist will look like that. You see, it's like would be ones, it will be stiff lattice. But the probability to see this lattice is 1 over 2. Again, it's a little bit higher, but we'll never randomly generate it. So we need to kind of improve. Right. If it's broken, it's broken, doesn't matter. We need to improve that, and that was the last actually image that I wanted to show you, and unfortunately I think the computer doesn't want to do that. Just switch pult and then this audio. Okay, doesn't matter. Doesn't work? I think we're almost done, so it's not a big deal. Yeah, it something wrong with the projector. But again, at the end, I will upload this paper, and we will talk maybe about the Pareto things at the end. What actually is happening in this particular approach? You use CNN, your synthetic data on your generation. You generate some lattices, predict the properties, pick the best properties from these lattices, do genetic algorithm on them. It gives you a little bit lattices that doesn't exist in your initial training set. It's a little bit better. Then you took them, retrain neural network. So because your neural network right now will cover these lattices, then you do this multiple times. And if there is a chance to look at this image, you will see how your so-called Pareto front, the combination getting better and better and better. And at the end, this is already a combination of some sort of active learning, because each time you do this genetic algorithm by selecting something, by making some decision and getting new trained data set. And that's important, and that's exactly what we will cover. I think it's just did like that. Okay, it doesn't matter. It will give us quite good results at the end. So again, unfortunately, our devices are not working correctly. So on that note, we will stop because it's already late. Do you have any questions regarding this particular generative stuff? In the papers, we will discuss the reinforced learning and the generative learning that uses reinforced learning in the next lecture. And during the practice, we will do GANs this time. So we'll just play a little bit. And you already have, I think, in practice 9, notebook devoted to GAN, so you can play a little bit ahead of time. So on that note, I would like to ask you, first of all, to submit your home projects, or ask me a question if you have problems with the home projects. And 2, we're getting pushed by the administration of university to have a lot of students to evaluate the class. So I had a very nice slide showing that you need to do that, but I cannot show it to you. So please do that. We will do it again on the practice session when we will sit, and I will say 15 minutes, and we're just evaluating the class. Again, we need it, first of all, because we have already angry emails from the university saying only 3 people only 3 students evaluated the class. And second of all, it's also important for us to decide, should we continue with this class, should we modify it, or what's happening. So we would really like you all to evaluate the class. So please do that. We will centralize in a centralized manner. We'll do that on Thursday. But come on, it's 10 minutes. We wanted to do it today, but considering all these problems with equipment, we cannot. So thanks a lot. If you have any questions, ask. If you don't, we'll see you on Thursday. Good? Nice. Thank you.